Hi, I'm Kellen, and I'm going to walk you through my theory of most everything in physics. Now, you might be saying, theory of everything? That's a pretty stupid name. Yeah, theory of everything would be a stupid name. But in this case, it's actually pretty accurate. It is basically a theory of mostly everything in physics. Everything from quantum mechanics, to relativity, to turbulence, to field theory, just everything. And it all starts from my equation of motion, which I'm going to show you in just a second. And then you can derive all the existing physics that we know of from that, from my theory. And, you don't have to believe me, but if you're a physicist or a mathematician, you're going to want to see this. You're really going to want to see this. And I'm going to show you exactly how quantum mechanics and general relativity fit together, what's going on exactly with the Higgs boson, what the explanation is for dark matter and dark energy, and things like turbulence, entanglement, why quantum mechanics looks so random, but it's actually not random at all. It's like dice, like trying to throw dice, where, it's not random at all, but you're not necessarily going to be able to predict it. So that's what's at the root of things, like entropy, and we're going to go and look into that with more detail. But again, the existing physics, are they wrong? Well, yes and no. They are wrong if you try and take them too far. Oh, lovely garage noises. I'm filming this in the garage, by the way, so, I mean, the video quality is amazing, isn't it? But it is what it is. I'm working with what I got here, so I'll run with it. And I'll show you that really existing physics are only approximations. And I'm going to show you how. I'm going to give you the equations that you can use when existing theories fail. And so I'm going to show you all the equations in just a second, and then I'm going to go through them all in great detail. So here we go. Okay, here are some of the equations. I'm just showing them to you, so if you are familiar with physics or math or whatever, then some things will dawn on you. But let me just explain the concepts while I'm at it, and then I'll explain everything else in more detail. So anyway, the fundamental principle is really conservation of motion. This is what's going on. This is the fundamental equation that I'm giving you, from which everything else follows. Really, this would be an axiom of physics. So, and by the way, I guess you'll know me as this stick from now on for the rest of the videos. I'll just shake it and point at things and go crazy with it. But that way you can see stuff. Real high tech, real high tech. So anyway, motion. Well, you'll notice that there are a couple things going on here. This is the speed of light, really the speed of space, we'll see. This is the velocity that you usually are familiar with. It's really radial velocity. And this is the radius or distance. And this is this angular velocity, this omega. Well, usually people throw time in as an extra dimension, and then that whole new mathematical object called space-time would have curvature. Really, all it is that your path through space can have some curvature. That's all it is. We're going to see that. And so that's this thing that people are talking about and misunderstanding, really, thinking that this space-time thing is curved and they don't really understand what's going on. It's really that the path through space can have some curvature. And we're going to explore that and show that that's really what's going on. And so this is the way to put distance. This is for velocity. This is the angular velocity. This is that curved velocity. And you can see they're similar. So we can really, this is just like a circle. We can parameterize this like a circle with sines and cosines. And that's what we're doing. And it makes everything really easy. Where people run into problems is when they try and pull this apart arbitrarily and just use x, y, and z without really knowing what's going on behind it, the fundamental concepts. And that's the important thing, because that lets you really understand what's going on. And so I'm going to explain that more. I'm going to explain the Big Bang, what happens with that. I'm going to go through and show force, that it's really all the same thing. So unifying all the forces, putting them all together. I'm going to show you exactly how to do that and exactly where that comes from. Now, I'm also going to explain things like dark matter and dark energy and all that stuff, black holes, and we're going to see, well, what is the observation when astronomers look out at the sky, what do they observe? What do they actually see? And what math, what equations, what theories lead them to predict different things? So we're going to really examine that and see what's actually happening. And these equations, this is just some of them, but these are going to allow us to do all that. And so we're also going to look at this phase angle. This is this theta here going on. And this is the spin. I'm going to show you this is really spin. And we're going to use this in quantum mechanics and quantum field theory and everything, and show what's going on with entanglement and phase transitions and why quantum mechanics really isn't random. It's like dice. It's like throwing dice. It's not random, but you're not necessarily going to be able to predict it. So I'm going to show you exactly how that happens with chaos theory and the logistic math and all that business. And this is a time dilation factor. And the important thing here is that nobody knew that this should have a plus or minus in it. They usually just have this without the plus or minus and call it the Lorentz factor and use it in relativity. But it's really this. It's this 1 over this sine theta. And this is really important because we're going to see that this has everything to do with things like antimatter and why people are confused about the exclusion principle with electrons and what's going on with the nuclear interactions and different things like that. And it really comes from this. And furthermore, we're going to see that this is really what's going on behind the Higgs boson and the graviton and everything like that. So I'm going to show you exactly what's going on. Now this is the coupling factor. People call it a coupling constant. It's not a constant. And they know it's not a constant because in the parlance of particle physics, they do something called run. They change. And this is what leads people to think that, well, maybe all the forces unify at some high energy when they graph it all out. But the thing is, they're breaking up this alpha into arbitrary parts, and then they're seeing, well, they should be the same thing at some point because they are the same thing. They exactly are the same thing, and I'm going to show you why and how. So this is charge. I'm going to show you why this works out this way, how a photon, something moving at the speed of light, if this cosine is plus or minus 1, this sine is going to be 0. That means the charge is going to be 0. That's why photons have no charge. And so I'm going to explore that and show you more of exactly how that works. Now this is the proper time, that people call it tau. If you're familiar with relativity, then you would know proper time would be the time ticked off by a clock going along with whoever's being observed. So this is the rate of change between the target's time and the observer's time. It's really how the target's time and the observer's time is synced up. At everyday low velocities, this is about 1, so it doesn't make any difference. But then when you get really high, when you get to really high velocities, start going really fast, this makes a huge difference. And it's the same thing with this gamma. It's just 1 over the sine theta. So it's the sine theta and this thing too. So it's a bunch of different ways to write the same thing, but we're going to see how the timing between things really affects what it is, how we think it's in terms of matter or antimatter, or whether we think it's light, or whether we think it's a Higgs boson or a graviton. I mean, I'm going to show you that really they all come from the same thing. I'm going to show you exactly what's going on. So, without further ado, let's get on to the next slide and keep going. So this is what momentum is, and we can write the energy in these different forms. This is the kinetic plus the potential. So we can see this is really the kinetic energy. It's not 1/2 mv squared. It's this right here. And that makes a huge difference. And we're going to see and explore exactly what the consequences of that are. So we can also express what this phase angle is again and write it in this form, which we're going to use when we get into phase transitions and entropy and things like that. So these are other ways we can write it. And this is a relation between all those different variables and whatnot. So this is what this n is. We're going to use that in entropy. This is another way to write the distance. And so this big R is time invariant distance, just in terms of the energy. So we'll use that. This is what the Lagrangian is, the kinetic minus the potential, and it's this form. And we're going to see that not recognizing that this is what the Lagrangian should be, that gives you a whole lot of grief when you try and figure out what's going on with like the Higgs boson mass and different things like that. You're going to get these correction factors, and you'll think that this, quote, Higgs boson needs a mass of exactly this amount because your equations are wrong by exactly that amount. So I'm going to show you exactly how that works. And this is the uncertainty principle, the quote uncertainty principle. I'm going to explain this more, but you can see where it comes into it. People usually don't know that this sine 2 theta is hanging out, and this makes a huge difference, and this is what's involved in phase transitions. We'll get into that later. These are ways to write the time if you want to write them in more complicated form, but this is the time according to the observer and time according to the target being observed. And with matter and light, well, at the start of our observation, the very start, well, we'll have to pick a time, so we can say time is 0 at the start of our observation. So then the angle is just this. Well, if the velocity is 0, then that means the cosine 0, that means the sine is going to be plus or minus 1. Well, if it's 1, we're going to get what's called a spin 1/2. If it's minus 1, we're going to get spin minus 1/2. Or people like to make up silly names that don't really explain anything to you, like fermions and bosons. Really, it's just this. It's just saying, well, if it's stopped and you can measure it and everything, then it's going to look like it has this spin, this intrinsic angular momentum of 1/2 or minus 1/2. And you can also see that this sine theta makes it clear. Remember, that's a measure of the phasing between the target and the observer. If it's this one, then the target's time is moving on exactly with the observer's time. But if it's this one, then the target is experiencing time exactly opposite to the observer. And that's why things look like antiparticles or particles. And things look like they're matter and antimatter. And if you put these together, then you get a spin 0, or spin 2 of these, you get a spin 1. So that's what looks like particles and antiparticles colliding and annihilating and forming photons and all that stuff. That's really what's going on, and I'll explain that a little more. What if it's actually moving at the speed of light? Well, then this sine is going to be 0. The cosine will be 1 or minus 1. If it's 1, then this spin is going to be 0, or actually, equivalently, 2. It's just like a clock. If you go around once, then you're back at 12 o'clock. The same thing happens with angles. And so people interpret, if it's just 0, they interpret that as a Higgs boson. If it's 2, they interpret that as a graviton. But it's really the same thing. It's the same thing. It's something moving at the speed of light. It actually has no mass. The reason people think a Higgs boson would have mass is because their Lagrangian is off, because they don't recognize this, and their Lagrangian is off by a certain amount, an exact amount, and that's what they think the mass is supposed to be. And I'm going to show you exactly what's going on with that. But if it's this one, if it's minus 1, then it's going to be a spin 1, or equivalently spin minus 1. What people normally think as a photon. But these are both photons. This is a photon moving towards you, because you're measuring distance outwards. So with the minus velocity, it's moving towards you. This one is a photon moving away from you. Now, if something emits something away from you, then the rest of it, by conservation of motion, has to move towards you. And that is going to look like an attractive force, or like something is gravitating with mass. That's why people think that the Higgs boson has to do with mass, and that the graviton is causing things to gravitate. It's really just light. It's this simple. It's just this. Something emitting a photon away from you, the rest of it's going to move towards you, and that's going to look like an attractive force. Now, with what people ordinarily think is the photon, is this one, a photon moving towards you, they think that that's just involved with electromagnetism, with charges. Well, if this emits a photon towards you, the rest of it is going to move away from you. That's going to look like a repulsive force, or, for example, like charges repelling each other. That's what this is going to look like, and that's why people think that the photon is the mediator, of the electromagnetic force. But really, it's both of this. It's both of these are light, and both of these are matter. And there's really no distinction, and that's why people get confused with the exclusion principle, the Pauli exclusion principle, with fermions and bosons and what's going on, and they really don't have this picture clear, and this is all it is. And when you have mistakes up in your Lagrangian, when you try and calculate equations of motion, then they're going to be wrong by certain amounts, and you're going to be able to make predictions that, yeah, your equations are wrong by certain amounts. And I'm going to show you next what is going on with forces. And furthermore, this angle over here can go through anything. I mean, we just, at the start of our observation, this time is 0, but then this angle can change and go through all sorts of things. And so these can all change, and that's why people see what they interpret as particles and antiparticles annihilating to form photons, and particles popping in and out of energy and all this, crazy stuff that people aren't understanding. It's really just this. This is what's going on behind it, and I'll explore that a little more. So, these are a bunch of different ways to write force. It's just F equals ma, but from the equations I gave you, you can look and see that these are all just different ways to write the same thing. But if you don't realize that they're the same thing, you're going to think they're just completely different forces. For example, this one is the pattern that string theorists recognized looking at the strong, quote, strong nuclear interaction. They saw this pattern right here. And if you take the potential, meaning you put an extra r in front of this, then it's going to grow linearly with distance, the potential energy will. And so that's going to look like a spring or a string. And this is what's going on. Also, you see that there's just a constant here. This would also look like a scalar field or a Higgs field. So this is where people also get that idea. And if your equations of motion aren't right, if your Lagrangian is off, then you're going to have extra terms like this appearing in there. And so you're going to think that you need an extra particle with a certain mass and blah, 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 but it's really just this going on behind it. That's all it is. And you can also see in this form, it's what you know as centrifugal force right there. This is an inverse square relation that people notice and recognize in a lot of forces. I mean, people say like, oh, magnetism and gravity, they look pretty much the same. It's because they are the same thing, guys. They're the same thing. And you can just write it in a bunch of different ways. You could write it this way with an energy factor and a, quote, coupling constant here. You can write it in this form with just with this r being just a function of energy only. This little r is the actual true distance. And this form is the electromagnetic form. And we can break this up into electricity and magnetism forces, and we'll do that later. But you can just look at it from right here and see, well, this r squared is always positive. This alpha is sine squared. That's always positive. So, or 0. So if you just try and plug in charges, well, if you plug in opposite charges, you're going to get an overall minus sign out front. And what that will do is that will give you an attractive force. With an overall minus sign, that will give you an attractive force. But if you plug in charges that have the same sign, then the minus sign will either cancel, or you won't have one in the first place, and you won't have an overall minus sign. So it won't be an attractive force, it'll be a repulsive force. That's why it looks like similar charges or like charges repel and opposite charges attract. That is what's going on. It's just this right here. And I'm going to go through and derive electromagnetism for you too. And this is yet another way to write it, which will show up in, nuclear forces and different things like that. It's really all the same thing, Now for gravity, people write it in this form with this g up here and think that this g is constant. Well, we can look right here and see this g, there's no way it can be constant, no way. And what are the consequences of that? Well, we know the g is going to be this. We can put it in this form, where this big R is just in terms of the energy. And we can throw a few other things on the other side and put it in this form. And you might not recognize it at first, but this is really the Einstein field equations for general relativity. That's what this is. This is the cosmological constant, quote constant, not really a constant. This is the, quote, Newton's constant, not a constant. And this is the, quote, stress energy tensor, if you put it in tensor form. And you can see, well, if you don't realize that this is a variable, if you think it's constant, then you're going to have to add in another term over here to correct for that, which is going to have energy in front of it, which, if you're putting it in tensor form, you're going to have to include curvature tensors. And that's what's going to happen. You're going to have problems with it. And this is also why people have had such difficulty putting together quantum mechanics and general relativity. It's because this g is not actually a constant. And furthermore, with quantum mechanics isn't random. It's just the fact that it's hard to predict. It's in terms of sines and cosines. And as we saw, well, if we want to stop something and measure it and say it's actually a particle, it's stopped, well, that only happens when that angle is at certain values. So when you look at it, it's going to appear quantized. If you're trying to measure things, it's going to appear quantized. That's what's happening. And I'm going to explain that and get into that a little more. So moving on, this is what temperature is. This is really the kinetic energy up here, divided by this entropy. It's this number of things. I'm going to explain that later. This is a Boltzmann constant, just a constant. And so this is entropy. And it's usually in the, people don't recognize that this is what it is inside here. And so they encounter a lot of so-called anomalies and things like the corona of the sun not being what temperature they think it is. And we'll get into that more. This is pressure, force per unit area, the gamma. This is volume, distance cubed. This is the stress, which we'll use later in fluid dynamics. This is density, mass per volume. This, if it's constant, and we'll look at that later, that is going to explain dark matter. This right here is actually explaining dark energy. So there you go. This is kinematic viscosity, and this is this energy dissipation rate. And we'll get into that more with fluid dynamics. This is Reynolds number, has to deal with turbulence and turbulent flow. And we see it's really just this is the ratio between the radial velocity and the curved velocity. And if you square it, then you can just put it in terms of alphas, a unitless thing. So we'll get into that more later. And this is just putting together the thermodynamic variables in terms of energy. And you might say, well, you've got some things missing. No, actually not. This is it right here. And you think you need to add other terms when you're doing old school thermodynamics because you think that you're supposed to have 1/2 mv squared. And so then you don't have all the energy you need, so you need to add another term. And so I'll explain what's going on with that later. And this is from turbulence, the Kolmogorov length or the characteristic length or whatever. It's really just this. It comes from how we showed what distance was or how we defined what distance was. And it works out to this. So I'm going to explore that later and show you what's going on. And that's a cat. You can see my awesome artistic skills. You know, that's too lifelike. I can't even believe this is just a drawing. So this is, I've showed you a whole bunch of math barf up on the boards. And so I'm going to get into it in much more detail and really go through it. So it's probably going to take a while, and I will get tired through it, but it's a video, and I mean, I know I personally would much rather watch a video than have to go through and read a bunch of stuff. But anyway, that's the explanation, and I'm sure there are going to be errors and whatnot in here, but I wanted to get this out and just let people know, because the concepts behind it are what are important. And clearing up a whole bunch of foggy business with physics. All right, so there's the overview. There's a lot of math stuff for you, so have fun with that. But in the next video, I guess I'll do the next video, I'll go into it in great detail, probably more detail than I'd like to do it, but it needs to be done. And yeah, I'm not a physicist or a mathematician or anything like that. I never publish anything. I don't have a degree in anything. But I couldn't just leave this in a notebook of mine somewhere. I had to let the world know. I mean, I'm just saying, here you go, peoples. Enjoy. I have no illusions about this being accepted. I fully expect people to come after me with torches and pitchforks, and for Stephen Hawking to come run me over in his wheelchair, and Einstein to rise from the grave as a zombie and to eat my brains. Either people will love it or hate it, or probably just ignore it, or maybe try and steal it, or try and say, oh, well, someone else already did all this stuff. It's like, dude, look, I did this from really from Maxwell's equations. The speed of light being constant in every reference frame. Really, I guess that's where Einstein started. I looked at the metric for special relativity and like, well, this is wrong. I'm just going to go back to speed of light. Really, the equations from like the Civil War time, like 150 years ago or something. And then I went through and derived them. Like, oh, this is right. Everything makes sense now. And went through and painstakingly went through all of physics, different parts of physics, and checked things and like, oh, okay, well, this explains that. Wow, they got this result for dark matter. Yeah, that's why. It's this theory that explains it. So that just happened in all sorts of things. But anyway, if you're a actual physicist or mathematician, I mean, have a field day with a video. And you know, I mean, it'd be cool to somehow make money off of this, but that's not what this is about, and it's not about high quality video or high quality presentation. I mean, come on, this is not high tech at all. So, well, it is what it is. I'll put a little contact email just for this, not my personal email, but just a contact for like this video, and you can shoot questions there. I'm not going to answer questions like on the video page because, I mean, it's like arguing with people on the internet. It's not a good plan of action. So if you actually want to like discuss something, I mean, I'm happy to do it. But like ideally, I'd rather discuss something in person. So you can go through the math painstakingly with someone and show them what's going on, or they can try and show me where I'm wrong painstakingly. So anyway, that's that. Hope you enjoyed it, and you can watch the next horribly long video. All right, bye. So here's the contact info, just kellenphysics@gmail.com. So if you have something that's not spam, then go ahead and send it on off and I'll try and reply. Anyway, hope you enjoyed it and take it easy.